Titrations are a great way to determine the concentration of a substance in a solution. It involves reacting one solution with another until they are at the exact stoichiometric ratio, meaning neither solution is in excess. Couple of quick definitions. The analyte is the substance in the flask, while the titrant is the stuff in the burette. If we add something that will make an observable color change, that's called an indicator. And while equivalence point and end point are often used interchangeably, they're not really the same thing. The equivalence point is the stoichiometric equivalence. As I said before, neither one is in excess. The end point is an observable color change. In a well-designed titration, these two are the same, or very, very, very close, but that needs to be a well-designed titration. And in second semester, we'll see how to actually do that. You need to be able to accurately read a burette in order to be able to do a titration. And when we read a burette, we read from the bottom of the meniscus, keeping in mind that the top is the zero. So we read how much has been added, not how much it contains. It's the opposite from a graduated cylinder. Also, we can see that the divisions are every 1/10 of a milliliter. And because we know we can estimate between the lines, our burette volumes will always be to the 100th place. So in this first one, it's between 0 and 1, and it's above 0.5, above 0.6, above 0.7, but less than 0.8. So I'm going to call that one 0.75 milliliters. Pause for a second to read the other three. You can see that all three of them go to the 100th place. Even if it's 0, it's 0.00. That lets us know the precision of the instrument. Typically, when we read a burette, we're going to read it before and after the experiment. So if I know the initial and final, I can figure out how much titrant was used. That's a simple subtraction, but I want to make sure that you see the significant figures. We are going to the 100th place every single time because it's a subtraction. At the end of a titration, we know 3 things and we need to figure out the 4th. We know the volume and molarity of the titrant and the volume of the analyte, so we can calculate the molarity of the analyte. Once in a while, we'll know the molarity of the analyte and calculate the molarity of the titrant. Here is the equivalence point in an acid-base titration. We're going to spend a lot more time on the shape of a titration curve later in the second semester. Titrations are stoichiometry problems. They're using solutions instead of solids, so typically we work with molarities, but we can actually mix them up and use grams as well. Let's take a look at a titration calculation. In general, the molarity of our substance B, whatever it is the volume of our first one times its molarity. Use the stoichiometry from the balanced equation and divide by the volume of our stuff we want to figure out. So first we need the balanced equation. We need to do some solving. Use sig figs and units. So for my first example, I want to know the molarity of HCl titrated with barium hydroxide, and I'm going to take a look at my balanced equation. Often you'll find molecular equations are more helpful, We'll also take a look at a couple that use net ionic. But you can see that there's a 2-to-1 ratio in this equation. So then I set up the stoichiometry. Take my volume of barium hydroxide and its molarity. Here are the mole ratios from the balanced equation. Divide by the volume of hydrochloric acid. Note that I don't have to convert to liters here because the milliliters end up canceling out. Plug in the numbers and I get to 0.253 molar. This doesn't work with just acids and bases, however. In my second example, I want to know the molarity of hydrogen peroxide, and it can be titrated with nitric acid. So first I need to look at my balanced chemical equation, and these are in a 2-to-3 ratio. So I draw my crossbars, and I see that I end up with 0.463 molar hydrogen peroxide. Give these 3 problems a try, and when you're ready, we'll take a look at them. All right, let's take a look at the first problem. The first one, you should have been able to write the balanced equation. And these are in a 1-to-1 ratio, which makes it a little easier. Volume of NaOH times its molarity. Balanced equation lets us convert to acetic acid, divide by the volume of the analyte. The second one, here's the balanced equation. It's a lot more complicated. So let's take a look at this problem. The first thing I did was find the molarity of oxalic acid. Grams divided by volume divided by the molar mass gives me the molarity. The other thing that's unique about this problem is that I'm starting with my volume of analyte because that's the only one where I know the analyte and the molarity. Then I use the coefficients from the balanced equation and divide by my volume of titrant, the permanganate. Note that I'm using potassium permanganate and the net ionic equation uses permanganate ion, but they're in a 1-to-1 ratio, so it doesn't really matter. And for the third one, we're looking at a triprotic acid, phosphoric acid, so it's an acid-base titration, but it's a 3-to-1 ratio. So it looks pretty similar to the one at the top, but the stoichiometry is different. So that is how we solve titration problems. We are going to talk about pH indicators more in the second semester, but pH indicators are weak acids, but they're unique in that they change color when the pH changes. So litmus, one of the earliest pH indicators, is pink-red when it's an acid, blue when it's a base. Bromethymol blue, another common one, is yellow in its acidic form, blue in its basic form, and green when neutral. Phenolphthalein, one of the most common for weak acid, strong base titrations, is colorless and then pink. And then methyl red changes from red to yellow, depending on the pH. Again, we'll talk about these in more detail and the chemistry of it second semester. And one of the more popular pH indicators that you might see in middle school is red cabbage, where its color changes with varying pH. So I hope this brief introduction to titrations was useful, and as always, if you have any questions, let me know.